वेलकम टू वी लर्न में आपका स्वागत है। सब्जेक्ट ऑपरेशन रिसर्च सेशन नंबर 12। टॉपिक टू बी कवर्ड इन दिस सेशन क्यूइंग मॉडल्स। इंट्रोडक्शन, कैरेक्टरिस्टिक्स ऑफ क्यूइंग मॉडल, notation and symbols, statistical methods in queuing, the MMI system, then the MMC system, then the MEKI system, and last one is decision problems in queuing. Now introduction. In queuing problem is identified by the presence of a group of customers who arrive randomly to receive some service. आप देखते हैं कि बहुत बार बैंकिंग ऑर्गेनाइजेशन या हॉस्पिटल या फिर टोल ब्रिज के पास में बहुत लंबी लंबी लाइनें लग जाती हैं। उन लाइनों की को कम करने के लिए कि हाउ दे आर रिड्यूस्ड, तो हम जो है क्यूइंग सिस्टम का यूज करते हैं। और क्यूइंग सिस्टम से हम ये आइडेंटिफाई करते हैं कि अराइवल रेट क्या है और सर्विस रेट क्या है। अगर हम सर्विस रेट को बढ़ा देते हैं तो डेफिनेटली जो है आपकी क्यू कम हो जाती है, या फिर हम कोई भी विंडो को बढ़ा दिया जाता है तो भी आपका क्यू रेट कम हो जाता है। तो ऐसे केसेज के लिए ये सिस्टम हम यूज करते हैं। द कस्टमर अपॉन अराइवल मे बी अटेंडेड टू इमीडिएटली और मे हैव टू वेट अंटिल द सर्वर इज फ्री। द सर्विस टाइम रिक्वायर्ड टू सर्व द कस्टमर्स इज ऑल्सो ए स्टैटिस्टिकल वेरिएबल्स। The queuing models are basically relevant to service-oriented organization and suggest ways and means to improve the efficiency of the service. An improvement of service level is always possible by increasing the number of employees. Queuing methodology indicates the optimal usage of existing manpower and other resources to improve the service. It can also indicate the cost implications if the existing service facilities has to be improved by adding more servers. The relationship between queuing and service rate are this one, like cost of waiting is below, then cost of service, and last one is a cost of operation. You have seen that the cost of waiting curve is like as a demand curve given in economics, and cost of service is like as supply curve. दोनों को अगर मिक्स कर देते हैं तो cost of operation हो जाता है। A queuing system can be described by the following components. सबसे पहले हम अराइवल लेते हैं। अराइवल क्या है कि कस्टमर कितनी देर में या उनका जो आने का रेट है पर मिनट पर आवर्स कितना है, कितने कस्टमर एक मिनट में आ जाते हैं, उसको हम अराइवल रेट कहते हैं। एंड इट इज डिनोटेड बाई ग्रीक लेटर अल्फा। द स्टैटिस्टिकल पैटर्न ऑफ द अराइवल कैन बी इंडिकेटेड थ्रू द प्रोबेबिलिटी डिस्ट्रीब्यूशंस ऑफ द नंबर ऑफ अराइवल्स in an interval. This is a discrete random variables. Service, the time taken by a server to complete service is known as service time. The service time is a statistical variable and can be studied either as the number of services completed in a given period of time or the completion period of a service. Server, the service may be offered through a single server such as a ticket counter or through several channels such as a train arriving in a station with several platforms. Sometimes the service is to be carried out sequentially through several phases known as multi-phase service. Time spent in the queuing system. The time spent by a customer in a queuing system is the sum of waiting time before service and the service time. And now characteristics of a queuing model 3. Queue disciplines. The queue disciplines indicates the order in which members of the queue are selected for service. It is most frequently assumed that the customers are served on a first come first served basis. This is commonly referred to as FIFO system. That means first in first out. Occasionally a certain group of customers receive priority in service over others even if they arrive late. This is commonly referred to as priority queue. The queue discipline does not always take into account the order of arrival. The service chooses one of the customers to offer service at random. Such a system is known as service in random order 0. Size of population. The collection of potential customers may be very large or of a moderate size. Maximum size of a queue. Sometimes only a finite number of customers are allowed to stay in the system, although the total number of customers in the population may or may not be finite. Like this one, this is a service facility 1, 2, 3, 4 and arriving customers 1, 2, 3, 4, 5, 6 and this is a queue and then departing customers. Notation and symbols. Kendall 1951 has introduced a set of notation which have become standard in the literature of queuing models. A general queuing system is denoted by A, B, C and D, E, where A probability distribution of inter-arrival time, B equal to probability distributions of service time, C equal to number of servers in the system and D equal to maximum number of customers allowed in the system and E equal to queue discipline. Notation and symbols. The behavior of the queuing system will depend upon time. Such a system is said to be in transit state. When sufficient time has elapsed since the beginning of the operations, the behavior of the system may become independent of time. The system then is said to be in a steady state. Notation and symbols 3. The following symbols will be used while studying queuing models. N equal to number of units in the system who are waiting for service and who are being served. P and T equal to transient state probabilities of exactly n customers in the system at time t, assuming that the system has started its operations at time 0. Pn equal to steady state probability of having n customers in the system. Notation and symbols for x equal to mean effective arrival rate, mu equal to mean service rate per busy server, c equal to number of parallel servers and wt equal to density functions of the waiting time, ws equal to expected waiting time per customer in the system including the service time, wq equal to expected waiting time per customer in the queue excluding the service time, and ls equal to expected number of customers in the system including those who are receiving service, lq equal to expected number of customers in the queue excluding those who are receiving service. Statistical method in queuing. The arrival of customers, the departure of customers after service and the waiting time of a customer before being served in a queuing systems are random phenomena. In order to develop appropriate statistical models of this problem, the following assumptions are made. If nt denotes the number of arrival or departure after service in the time interval 0 to t, then nt has independent increments. If there are n units in the system, the probability of exactly one arrival from 1 t to t plus delta t is lambda n delta t plus 0 delta t. Likewise, the probability that exactly one department or one departure after service will occur from t to t plus delta t is mu n into delta t plus 0 delta t. The quantity 0 delta t represents a functions of delta t such that limit t equal to 0 delta t or q delta t upon t equal to 0. If there are n customers at time t, the probability that the number of arrival and departures combined will exceed 1 during the time interval t to t plus delta t is 0 delta t. Poisson process. It can be shown Taha 1971 when delta n equal to delta, when mu n equal to 0 for all n that under conditions 1, 2 and 3, the probability p and t of having exactly n customers in the system, assuming that there is no customer in the system at time 0, is given by p and t equal to delta t to the power n e minus delta t upon factorial n, where n equal to 0, 1, 2. If the service component is ignored, the number of arrival in the interval 0 t has the probability distribution of a Poisson variables with parameter lambda t, which is the product of the arrival rate and the length of the interval t. This probability law is known as the Poisson process. Relationship between Poisson process and exponential probability distribution. Consider a queuing model in which the number of arrival in an interval of length t follows a Poisson process with arrival rate lambda. If the inter-arrival times are independent random variables, they must follow an exponential distribution with density functions of t, where functions of t equal to lambda e minus lambda t, where t greater than 0. If the inter-arrival times in the queuing systems are independently, identically distributed exponential random variables, then the number of arrivals in interval follows a Poisson process with arrival rate identical with parameter of exponential distribution. Consider a random variable x with an exponential probability distribution. Then for s t greater than 0, p x greater than t plus s x greater than s, which is equal to p x greater than t. The MML system, in this queuing model, it is assumed that the number of customers arriving at a time interval t follows a Poisson process with parameter lambda. Equivalently, the interval between any two successive arrivals is exponentially distributed with parameter a. The time taken to complete a single service is exponentially distributed with parameter mu. The number of server is 1. This probability distribution is known as geometric probability distribution, where Pn equal to P, number of customers in the system, equal to N, which is equal to lambda upon mu to the power N, 1 minus lambda upon mu, where N equal to 1, 2, 3, 4, 5. So P0 equal to 1 minus lambda upon mu, and lambda upon mu is called traffic intensity. Probability distribution of waiting time in an MMI system. Let T be the time spent by the customer in the system based on first in first out service discipline. If an arriving customer find it persons ahead of him in the queuing system, then T equal to T1 plus T2 plus T3 plus and so on Tn plus 1. By lack of memory property of the exponential distribution, T1 is also distributed as an exponential variable with parameter mu. Thus, T is the sum of n plus 1 independently, identically exponentially distributed random variables. The density functions of T is a gamma distribution whose density function is W T upon n plus 1, where W T upon n plus 1 equal to mu T to the power n upon factorial n e minus mu T greater than 0. The density functions of the total time Wt can be computed by first multiplying the expression of Wt upon n plus 1 with the probability that there are n customers in the system, and then summing over all values of n from 0 to infinity. The density functions Wt is thus Wt equal to mu minus lambda multiply E minus mu minus lambda, where T greater than 0. The total time of customers in the system follows an exponential probability distribution with parameter mu minus lambda. The customer starts receiving service immediately after his arrival. If there is no customer in the system, thus Pt equal to 0 equal to P0 equal to 1 minus lambda upon mu. In this queuing model, it is assumed that the inter-arrival times are independently, identically exponential distributed random variables with a common parameter a. The service times are independently, identically, exponentially distributed random variables with a common parameter mu. The number server in the system is C greater than equal to 1, so that service can be provided simultaneously to C customers. The infinite server queuing system is limiting behavior of an MMC model. When each customer is served immediately on arrival, such a situation is conceivable when the customers are using self-service. There is no waiting before the start of the service, so that LQ equal to 0 and WQ equal to 0. As C approaches to identify the steady state, probability are given by 1 upon P0 equal to summation of equal to 0 infinity lambda upon mu to the power n divided by n factorial, which is equal to E lambda upon mu. P0 equal to E minus lambda upon mu, and Pn equal to E minus lambda upon mu multiply lambda upon mu to the power n divided by factorial n. The steady state probability Pn, indicating that there are n customer in the system, is given by a Poisson distribution with parameter a upon mu. And now the MEKI system. In many queuing model, the service consists of a number of phases. Example, the repair of a certain machines may require a number of sequential steps. The time taken at each phase of repair is a random variable following in exponential distribution with parameter mu. Let there be k phases, the service time of the ith phase being s I equal to 1, 2, 3 plus and so on k. The total service time s can be expressed as s equal to s1 plus s2 plus s3 plus and so on sk. The gamma distributions is also a member of Erlangen of distribution and is denoted by ek when k exponential variables are involved. Both the exponential service time distribution and constant service time distributions are special cases of Erlangen service time distributions with k equal to I and k equal to minus I respectively. In between there are service time distributions of various types. Now this one, each number of the Erlangen distributions has the same mean 1 upon mu. The mode is at t equal to 0. For k equal to 1, it is t equal to 1 upon 2 mu. For k equal to 2, in general, the mode is located at t equal to k minus 1 upon k into mu. The variance of the kth member of the family is 1 upon ku square. Thus, given the data of service distribution, we may approximate it by a member of Erlangen family using a suitable value of k. The expected number of customers in the queue, LQ, expected waiting time before being served, WQ, and the expected number of customers in the system, LS, and the expected time spent in the system, WS, are given by LQ equal to 1 plus k upon 2k, which is equal to lambda square upon mu minus lambda, WQ equal to 1 plus k upon 2k multiply lambda upon mu minus lambda, and WS equal to WQ plus 1 upon mu, and LS equal to lambda multiply WS. As k approaches to identify the queuing system represents an arrival pattern which follows Poisson process with arrival rate and constant service time P per customer. The expressions of LQ, WQ, WS and LS are given by LQ equal to lambda square upon 2 mu minus lambda, whereas WQ equal to lambda upon 2 mu minus lambda, WS equal to lambda upon 2 mu minus lambda plus 1 upon mu, and LS equal to lambda square divided by 2 mu minus lambda plus lambda upon mu. The study of queuing models help us to find the ways and means for improving performance of the queuing system. A common viewpoint is to base the decision on a cost model which minimizes the sum of cost of service and of waiting time per unit time. The service can usually be ascertained from the various available records. Decision problems in queuing. Consider a single server model with an arrival rate A and service rate mu. It is assumed that the service rate mu is controllable and it is required to determine its optimum value based on an appropriate model. Let Ci equal to cost per unit increase in P per unit time and C2 equal to cost per unit time per persons of waiting. So decision problems in queuing, the total cost of average waiting and service per unit time is T mu equal to T1 mu plus T2 LS. In an MMI or FIFO system is follows that T mu equal to T1 mu plus C2 lambda upon mu minus lambda. The optimum value of mu is obtained by minimizing Q mu with respect to P by calculus methods. This value is given by mu equal to lambda plus C2 lambda upon C1 to the power 1 by 2. And now do it yourself. Question number 1, explain 5 the MML system, and question number 2, list characteristics of a queuing models, and that's it from session number 12. Thank you.